Welcome to our exploration of relations and functions. In this chapter, we'll discover how elements from two sets can be paired and how these pairs form the foundation of mathematical relations. Think about everyday life. Each hour of the day is paired with a temperature, or a teacher pairs student scores with the number of students. These pairings help us understand data and relationships more clearly. By the end of this video, you'll understand not only how to create these pairs but also how to identify special relations called functions. Let's begin our journey into the world of sets, pairs, and the connections between them. Let's start with the Cartesian product. Given two non-empty sets A and B, the Cartesian product is the set of all ordered pairs where the first element comes from A and the second from B. For example, if A is 1, 2, 3 and B is 4, 5, then the Cartesian product of times B is 1, 4, 2, 4, 3, 4, 1, 5, 2, 5, 3, 5. Notice how every element from A is paired with every element from B. This concept is foundational for understanding relations, as it gives us all possible pairings between two sets. Ordered pairs are central to relations. Two ordered pairs, say x, y, and uv, are equal only if their first elements are equal and their second elements are equal. For instance, 2, 5 equals 2, 5, but not 5, 2. This strict order is what makes the Cartesian product unique and useful in mathematics. It helps us distinguish between different types of relationships and ensures clarity when working with sets. How many pairs are in a Cartesian product? If set A has p elements and set B has q elements, then the Cartesian product of times B contains p times q pairs. For example, if it has 3 elements and B has 2, then there are 3 times 2 equals 6 pairs. This multiplication principle helps us quickly determine the size of the product set, which is useful for understanding the scope of possible relation. The concept of the Cartesian product can be extended to more than two sets. For example, A times A is the set of all ordered triplets, A, B, C, where each element comes from set A. This idea is crucial in higher mathematics, especially when dealing with three-dimensional spaces or more complex relationships. Ordered triplets follow the same rule: the order and the elements matter. Relation from set A to set B is simply a subset of the Cartesian product A times B. This means we select certain pairs based on a specific relationship between their elements. For example, if we want all pairs where the first number is a factor of the second, we only include those pairs. Relations help us describe and analyze connections between sets in a structured way. Every relation has a domain and a range. The domain is the set of all first elements in the relation, while the range is the set of all second elements, also called images. For example, if R equals 1, 2, 2, 3, 1, 2, 3, then the domain is 1, 2, 1, 2 and the range is 2, 3. Understanding domain and range is key to analyzing how elements are connected. Relations can be represented in several ways: roster form, set builder form, or visually using an arrow diagram. The roster form lists all pairs, while the set builder form describes the rule for the relation. Arrow diagrams provide a visual map showing how elements from one set connect to another. These representations make it easier to understand and communicate complex relationships. Set A has p elements and set B has q elements, then the number of possible relations from A to B is 2 to the power of p times q, or 2, pq. This is because each pair in the Cartesian product can either be included or not in a relation, giving us a huge number of possible relations even for small sets. Function is a special kind of relation. It's a relation from set A to set B where every element of A has one and only one image in B. In other words, no two pairs in the function have the same first element. This uniqueness is what makes functions so powerful in mathematics, as they provide a clear, predictable mapping from one set to another. Functions are often written as f x right arrow y, meaning f is a function from set x, the domain, to set y, the codomain. For each x in x, there is a unique y in y written as f(x). The set of all possible values f(x) forms the range of the function. This notation helps us clearly specify the direction and rule of the function. A real-valued function is a function whose range is either the set of real numbers r or a subset of r. If the domain is also r or a subset of r, it's called a real function. These functions are especially important in calculus and real analysis, as they describe relationships between real numbers. The identity function is one of the simplest functions. Defined as f(x) equals x for all x in R, it maps every real number to itself. The domain and range are both r. This function is called identity because it doesn't change the input value. A constant function is defined as f(x) equals c, where c is a constant real number. No matter what value x takes, the output is always c. The domain is r and the range is just the single value c. This function is useful for representing fixed values. Polynomial function is defined as f(x) equals a 0 plus a 1x plus anxn, where the coefficients are real numbers and n is a natural number. These functions are the backbone of algebra and calculus, describing curves and patterns in data. The domain is usually all real numbers. Rational function is a function of the form f(x) equals px slash qx, where both px and qx are polynomials and qx not equal to 0. For example, f(x) equals 1 slash x plus 2 is a rational function defined for all real x except x equals 2. These functions can have restrictions on their domains due to division by 0. The modulus function is defined as f(x) equals x, which gives the absolute value of x for every real number x. The output is always non-negative. The domain is R and the range is R plus 0. This function is useful for measuring distance from 0. Signum function is defined as f(x equals 1 if x0, f(x equals if equals 0, and f(x equals 1 if x0. Its domain is R and its range is 1, 0, 1. This function tells us the sign of a number, which is useful in many mathematical contexts. The greatest integer function, written as f(x(x), returns the largest integer less than or equal to x, for example 2, 7 equals 2, 1.2 equals 2. This function is also known as the floor function and is widely used in programming and mathematics. You can add two real functions f and g, both defined on the same domain x, by adding their outputs. F plus g, x equals f(x) plus gx. This operation creates a new function combining the effects of both original functions. The domain of the sum is the intersection of the domains of f and g. Similarly, you can subtract one function from another. F gx equals f(x) gx. This gives a new function representing the difference between the outputs of f and g for each in their common domain. A function can be multiplied by a scalar, which is just a real number. If alpha is a scalar and f is a function, then alpha x equals alpha times f(x). This scales the output of the function by the constant alpha, stretching or shrinking its graph. You can also multiply two functions. F gx equals f(x) times gx. The product function is defined wherever both f and g are defined. This operation is useful in many areas such as probability and calculus. The quotient of two functions is defined as f slash g, x equals fx slash gx, provided gx not equal to 0. The domain of the quotient is the intersection of the domains of f and g, excluding points where gx is 0. This operation is essential in calculus and rational expressions. Let's look at an example. If a equals 1, 2, 3, 4 and b equals 5, 7, 9, then a times b is the set of all pairs where the first element is from a and the second from b. The result is 12 pairs, showing how the Cartesian product expands possibilities. Similarly, b times a switches the order, and while the number of pairs is the same, the pairs themselves are different. Sometimes we need to find values that make two ordered pairs equal. For example, if 4x plus 3y equals 3x plus 5, 2, we solve for x and y by equating the first and second elements separately. This technique is useful for solving equations involving pairs. Relations can be defined with specific conditions. For example, if a equals 2, 4, 6, 9 and b equals 4, 6, 18, 27, 54, we can form pairs a b where a is a factor of b and a. This gives us a subset of the Cartesian product that meets our criteria. Given a relation R equals xy, y equals x plus 6xx, yn x6, we find the domain and range by checking which values of x produce natural number outputs for y. This process helps us understand the structure of the relation and its possible outputs. To determine if a relation is a function, check if every first element has only one image. For example, R1 equals 2, 3, 1, 2, 0, 2, 7, 4, 6 is not a function because 2 maps to both 3 and 7. However, R2 equals x, x, xr is a function because each has a unique image. Sometimes we need to find the domain where two functions are equal. For example, if fx equals 2x2, 1 and gx equals 1, 3x, we set them equal and solve for x. This gives us the values where the two functions intersect. For rational functions, the domain excludes values that make the denominator 0. For example, fx equals x slash x2 plus 3x plus 2 is undefined for x equals 1 and x equals 2. Always check the denominator to find the domain. To find the range of a function, determine all possible outputs. For example, fx x4 has range 1, 1, while fx equals sqrt 16 x2 has range 0, 4. Sometimes you need to solve for in terms of y to find the range. Some functions need to be redefined for specific intervals. For example, fx equals 1 slash x plus 1 for 2 less or equal to 2 can be broken into cases based on the value of x. This approach helps handle piecewise functions and ensures clarity in their definition. For functions involving the greatest integer like fx equals 1 slash x2, x6, the domain is where the denominator is positive. Solve x3, x plus 2 to find valid. This often results in intervals or unions of intervals. Multiple choice questions often test your understanding of domains. For example, fx equals 1 slash x, x is not defined for any real x, so the domain is empty. Always check for values that make the function undefined. If set A has q elements and set B has p elements, the number of possible functions from A to B is pq. Each element in A can be mapped to any element in B, so the possibilities multiply quickly. When adding or multiplying functions, the domain of the result is the intersection of the domains of the original functions. For example, if f is defined on 2, 5, 8, 10 and g on 2, 7, 8, 10, 11, then f plus g is defined on 2, 8, 10. Practice problems often ask you to compute Cartesian products, such as a times b or b times a. Remember, the order matters and the number of pairs is the product of the sizes of the sets. Try working out a few examples to reinforce your understanding. You may be asked to find relations like PQ times PQ for given sets. Use set operations to find the union and intersection, then form the Cartesian product. This strengthens your set theory skills. Some exercises ask for ordered pairs that satisfy conditions such as x plus y equals 5. List all possible pairs from the given sets and check which ones meet the criteria. This methodical approach ensures you find all valid pairs. Finding the domain and range of a relation or function is a common exercise. For example, if r equals xy, x2 plus y2 equals 25, the domain and range are the x and y values that satisfy the equation. Visualize or calculate to find all possibilities. Given a set of pairs, determine if it forms a function by checking if each first element is unique. For example, h equals 4, 6, 3, 9, 11, 6, 3, 11 is not a function because 3 appears twice as the first element. You may be asked to compute f plus g, x, f g, x, f g, x, or f slash g, x for given functions. Substitute the values and perform the operations, making sure to check the domains for validity. Objective and true-false questions test your understanding of definitions and properties. For example, does 5, 2 belong to r equals xy, y equals x5, or is a times b equals b times a? Practice these to sharpen your conceptual clarity. You've covered the essentials of relations and functions, from Cartesian products and ordered pairs to domains, ranges, and types of functions. Understanding these concepts is crucial for deeper studies in mathematics, as they form the basis for algebra, calculus, and beyond. Practice the examples and exercises to reinforce your learning, and you'll be well prepared for more advanced topics.